All right, so welcome everybody. I'm the president of this organization, and that should scare you right there. So our intention was to have a business meeting tonight, and if we don't reach a quorum, which is 133 members tonight, we will not be able to conduct our business meeting, and we'll postpone it till July. And we will continue the barrage of emails that all of you members have been getting. We might even go twice a week instead of once a week. So, like I said, call your friends that are MAS members, and have them at least join us on the Zoom call. Because as long as we can get them on by 7:30 or so, 7:40, or even by the end of the meeting tonight, we can wrap this thing up. So
how short are we?
Well, about 30.
Yeah.
About 30. If we had 30, we'd be good. So here's the list of the board members, the current board members. Here's our faces. So if you see us around town, feel free to say hi. I think all the board members are here tonight. Trina, John, Gunnar, Conrad, Matt, our treasurer. All right. Welcome new members. Steve Emmerich so kindly sent me a list of the list of new members. Welcome. Any new members in here tonight? Okay. I'm sure there's a new member or two online.
John Foley. I just moved to Minneapolis about a year ago.
Welcome, John.
Thanks.
And Bob Dorothy.
Online, welcome to the meeting. You know, this club is fabulous and fantastic. You know, they seem to ignore us when we have a meeting, but that's okay. We have great facilities, we have great turnout, we have great volunteers. You know, all of the mechanisms work fabulously. You know, our sites, the BSIG, our loaner scope program, you know, the board, we're all volunteers. I mean, this whole organization is run by volunteers. So my urging of you is, hey, if you can, if you're interested, get a hold of somebody from the board. We will help you get involved. Show up at a site. You know, Eagle Lake has a star party this weekend. Show up out there. They'll put you to work. You don't have to be a key holder to help out there. There's plenty of things to do. You know, point to scopes, whatever. So let's.
Hey, Mark, real quick.
So thank you very much.
David Chow, do you have a question? Online?
I was just saying I'm a new member.
Very good.
Volunteers, I'd like to thank personally Dave Faulkner and the Constitution Committee. You know, the Constitution and bylaws and articles of incorporation are all ready to go. We just need your help, members, to get that ratified. And I know there's been star parties going on at ELO. I know there was 2 BSIG events that were going on. There were volunteers there. You know, what can we say? Thank you, volunteers. Thank you for showing up and making those things run efficiently. And then all those behind the scenes that do, you know, maintenance. I mean, maintenance and cleaning and sweeping and moving out of cobwebs and things like that. You know, those people, you know, they make star parties happen and don't necessarily show up at star parties either. So thank you to all of them. All right, Dave Faulkner, you are up. And oh, by the way, I erased your presentation screen, so you're going to have to wing it. Or are you going to give me the next slide business?
That's fine.
I'm going to hide.
Good evening. Welcome, everybody. As of right now, we are about 21 people short of a quorum. So I don't know if it's going to go tonight, but one of the questions that came up to me was, so what are the differences between the old and the new? Just tell me, right? so all right, fine, we can do that. So what I'm going to go through tonight is just talk about the differences between the old and the new. Okay, without going into a lot of detail. I do have both the old one and the new one with me. So if we wanted to quote out of it, we can do that. But, again, let's just go through this. Just to reiterate, the reason we did this was because we call it the Constitution, but it's really the Articles of Incorporation and the bylaws were written 40 years ago. And there's been a lot of changes, both the state and federal statutes, as well as, the growth of the society itself. So it needed to be updated, and that's what we did. Like Mark said, I want to really thank all the people who worked on this. Also like to thank Jen Urban, who is our attorney on this, to help us put together a bylaws and articles of incorporation that reflect who we are today. Okay, and also is in line with all the state and federal statutes. Okay, so let's talk about what are the significant differences between the old and the new. And again, this is going to be kind of high level. So, but I'm going to stop after each slide. If you have a question, we'll certainly address that, because I don't want you to be voting for something that you have some questions about. All right. So the Articles of Incorporation are the agreement between the society and the state and federal government. Okay, and they are just the basic framework of the society and how it's structured. It's the bylaws that go into the details of that. Okay, so in the Articles of Incorporation, the physical address is now the lawyer's office. It used to be, I think, the Science Museum of Minnesota, but the physical address is really only used if someone is doing some sort of legal action against us. Okay, they don't send legal documents to a post office box. They send those to a physical address. And so now we have the lawyer's office as a physical address, which, if you're going to have legal action, is a good address to have. And then, but I say almost, really all of our correspondence goes to the post office box, even with the IRS. It all goes to the post office box. Okay. The next thing is the purpose. One of the things that we wanted to change was the purpose, because the purpose had, okay. Can you get the ballot off of there? All right. We had that we were organized for charitable, education, religious, and scientific purposes. And that "and" is a thing that held us from the state giving us a sales tax exemption. Changing it to "or," we're hoping is going to alleviate that, and then we can actually get an exemption to use from the sales tax for the things that we purchase for the various sites. The article around the conditions that restrict the operations of the society was expanded to get a little more detail about that. In addition, there's a section that was added that clarifies the actions that the corporation, which is the society, we are a corporation, is authorized to perform. The specific makeup of the board is not in the Articles of Incorporation. It refers to the bylaws for that. So we only got to update the bylaws on the organization of the society. We'll talk about that. The article on board member limited liability and indemnification is greatly expanded. That's why you incorporate in the first place, is to get any kind of liability off of individuals and place it on the society itself, so that individuals are not responsible, it's the society. And there's an additional article that goes into considerable detail around conflict of interest and the consequences associated with that for any member of the society, as well as a section on the policy around documentation and proceedings, financial documentation, audit, annual statements, stuff like that. Okay. Any questions about this? Any questions online? Going once, going twice. Okay. Moving on. Moving on. Why don't you? There's a question. Are we now able to advocate what? Advocate for dark skies. Yes, we can advocate for dark skies. We never were prohibited from doing that. So there's a question about whether or not that is considered to be advocating to legislature. That's a whole different story. Advocating for dark skies is not advocating to the legislature directly. We're just talking about what dark skies are about. This isn't working. Not on there.
That's not working. Okay, try it now.
Okay. All right. No. Okay. I hear that you were told that it's a fake news. Okay. The other fake news somebody said was that by advocating for dark skies, we're promoting the International Dark Sky Society, which is not a 501c3. In fact, it is a 501c3. We've checked on that, so it's all fake news. All right, bylaws. Now this is the details. This is where we get, the rubber meets the road. Okay, the differences. First of all, location and purpose are the same as in the Articles of Incorporation, so that's the same. And then we talk about membership and dues. Okay, we define the 4 classes of membership being regular members and patron members, student members, and honorary members, and how their payment goes. So, regular membership is the dues that is established by the society. Patrons are 2.5 times that. Students are half that, and of course, honorary members don't pay dues. Okay. Also, it's spelled out are the rights of the members, the membership duration, which is typically 1 year, resignation, suspension, expulsion, or sanctions associated with the society, and then reinstatement if you happen to hit one of those resignation, suspension, expulsion stuff. So all that's kind of spelled out. Any questions on that? Okay. Next, we talk about the meetings. Okay. Meetings of the voting membership. These meetings are where membership vote is required. So it's not a regular monthly meeting. It's like a business meeting. It's like this meeting. Okay. And the regular meeting. And so the meetings that we typically have that are considered voting membership meetings are the election, and then the business meeting where we talk about the budget, and then any kind of special meeting that is deemed necessary by the president to vote on something. So we actually want a membership vote. Okay. Notification of such a meeting shall be 5 to 60 days ahead of time by various means listed here. A quorum now, after we pass this, and I'll talk about that later, is 10% of the membership, which we would have met tonight. Voting is a simple majority. Okay, tonight we have to have 2/3 majority. That was not the hurdle though. Following requirements of membership voting are the election of the officers, ratification or rejection of the annual budget, membership dues, ratification or rejection of amendments to the Articles of Incorporation bylaws, and the ratification or rejection of merger, consolidation to another organization, a substantial sale of assets, and or dissolution of the society. Yes. Yes. That is a voting membership type meeting. Oh, I'm sorry. The question is, does that mean that we have to have a quorum for the annual election? Yes, that is considered to be a voting membership type meeting. So we have to have a quorum to do that. Okay. And the budget meeting too. Those are 2 big meetings that we have a year where you need to have the voting membership. And that's where the quorum and the simple majority after we pass these. Okay. All right. It's going to make it a lot easier for us to get some business done that way. On the officers, MS officers. So the principal officers are the president, the vice president, the secretary, and the treasurer, and they are considered the executive committee. Okay. In addition, there are the board members at large. We can have a total membership of anywhere from 3 to 15 members, and we can change that if we need to, but I think that's going to cover it pretty well for a while. They have to be 18 years of age, and they have to be in good standing with the society. Okay. The bylaws detail the duties of the president, the vice president, the secretary, and the treasurer, and the board member at large, including governing powers, direction around resignation, termination, leaves of absences, and vacancies. Here's one big change for all board members. Okay, the term after you're elected is 2 years, and you can have up to 3 consecutive terms, and then you have to take a year off. Okay, that's for all the board members now. Used to be just the president and the vice president had limitations. Okay. The board shall meet at least quarterly or 4 times a year. Special meetings may be called by the president or 1/3 of the board. And a quorum is 51% of the active directors. Directors being the executive committee and the other members of the board. Any questions on this slide? All right. Next, committees. There are 2 standing committees. One is the executive committee, which I just talked about, and the other is the finance committee, which consists of the treasurer. You can have more than that, but that's what it is right now. Yeah. And then there's other committees as designated by the board. Management miscellaneous provisions. The bylaws define the documents that are to be maintained for the society, the right to examine the books and records by the society by any member, periodic reviews to ensure the society is operating in a manner consistent with charitable purposes and with the proper documentation, proper filing with the Minnesota Attorney General, the Minnesota Secretary of State, the IRS, and any other governmental entity, although those 3 are the ones we typically deal with. And then the MAS properly engages in fundraising, which we've been pretty sticklers about. And then there's guidance around the society's publications, the media presence, as well as affiliations with other professional organizations, like the International Dark Sky Society. Okay. Any questions about this? Yes.
Obviously, the executive committee is on the board. The finance committee members have to also be on the board, and they be drawn from the.
Good question. I would think they would typically be board members. I don't know. But fortunately, I happen to have the document right here. So the question was, do the other members of the finance committee have to be on the board? Have to be like directors on the board? Okay. Be appointed by the board. But do they have to be board members? The board of, okay, so here's the paragraph on the finance committee. The board of directors, by resolution adopted by a majority of the board, may establish a finance committee. The treasurer is the chair, which includes at least 2 other individuals. The finance committee is responsible for developing and reviewing fiscal procedures, fundraising plans, and the annual budget with other board members. The board must approve the budget and all expenditures within the budget unless the budget is revised. Any major change in the budget must be approved by the board. Annual reports are required to be submitted to the board and reviewed in the annual meeting. So I would say not necessarily. Not necessarily. Yes.
Question about board members
Mhm.
just came up. Can they be on for 6 years and then go into a new term and a new position on the board? And the answer to that question is no.
No. So the way it's worded is you're in service on the board for a period of 6 years, and you have to be you have to step away from that service for a year, which means that's any position on the board. So you can't just move from one position to another and take another 6 years. You have to take a year off. Moreover, let's say that you were on a position, let's say board member at large for, let's say 4 years, and then you decided you wanted to run for vice president. So you went ahead and you got elected as vice president. You could only serve 1 2-year term as vice president because you would then have 6 years of service on the board and you have to take a year off. 6 consecutive years, right? Could be. Okay.
Oh, okay, thank you. Yeah, I should have done that. Yeah, I just wanted to chime in. This is Matt Dunham. That typically the finance committee role in the past has been managed by myself, and typically I'll meet either with Mark and or a couple other board members, or we have a full couple of board meetings to go through the budget, review everything before we present it to be approved.
Sure. Okay. Any other questions on this slide? Okay, I think we're to the point. Are there any other questions, period? Oh, okay. So here's the rub. We have to approve this articles of incorporation and bylaws according to the rules of our current bylaws. And our current bylaws require us to have 20% of the membership as a quorum for a meeting like this. And then we have to have a 2/3 majority vote to pass it. Okay. Well, we have 83 people on the line now.
Could I ask a question around this?
Yes.
This is Dave Evans. The membership is for the member and the family. In my
That's
case,
correct.
both my wife and I are online.
Different machines.
Different machines. So we can both vote correctly?
Well, you could try, but we're going to filter that out.
Okay, I didn't know if it was legal or not. It might be a way to get us to the appropriate number if it was something that was within our
No.
Constitution.
So now we're down to 81.
Sorry about that. Probably shouldn't have said anything.
All right. Dean's got a question here.
Oh, Dave, this is Bill Glass.
Just a minute, Bill. If
Sure,
we had
sure.
about, we need like, how many more people? 15? How many of us would have to temporarily resign to bring that down so we could have a quorum?
If we resigned, we couldn't vote.
Bill, go ahead. You're on.
On that question about multiple people voting that were in one family, the current Constitution has never been terribly clear about that. But the spirit that we've kind of always honored is that you get one vote per dues paying member.
Yeah,
So
that
even-
sounds fine.
So even though the other family members get to have the benefits of being part of the society, and for example, get loaner telescopes and such, you only get one vote for the dues that you pay. And we actually tried to clarify that in the new bylaws to
Right.
make it clear that family memberships still get only one vote.
So the gentleman who was on before, whose wife is also on, is she also a member?
No, she's, we've got, well, I guess like a dual membership.
Yeah. Okay.
Yeah.
Yeah.
I just thought it might be a way, but I understand our reasoning and it makes sense.
Okay. Any other questions?
I have a question on Article 7, Section 2 and 3. What's the term ex officio mean? I don't quite understand.
Ex officio means that they're automatically a member. So I think it deals with being a member of the board, right? So, so what's saying there, I believe, is that the executive committee is automatically part of the board. They are members of the board.
Oh, okay.
That's why I was saying that the board consists of the executive committee, okay, and all the board members at large.
Okay. And the non-voting seats on the board of directors?
Oh, so occasionally we have a student member on the board, but if they're less than 18 years of age, then they're not directors, so they're not a voting member.
Oh,
don't
I
have-
understand.
Yeah,
Thank
but
you.
we don't have any directors right now who aren't voted in and aren't voting members of the board. So You have another question there?
That's all I had. Thank you.
Yep. Okay. Thank you. Yes. Hang on a second.
Dave, I know you had in one of your second slides, how the differences were to move to the new, maybe instead of 20% moving to 10. But are we forbade from having this vote online over a period of 1 month of the entire membership? And move to a model that doesn't have us all meeting at the same time, even if it includes online? Is there verbiage in the existing, Constitution bylaws that would stop us from doing that? It seems like constantly get a mailing ballot in the mail for various investments and things where you have to vote for boards of directors, and everyone votes online now over a period of time. So it's just a suggestion or something we ought to consider, because I think you're going to run into this probably time and time again. And if we move to a different model.
I thought we discussed that with Jen. Did everybody hear the question? Did everybody hear the question? The question was, is there a way we could move this to an easier way? The problem is that it's supposed to be at a meeting. Okay. And if you do it over a month, you're not during a meeting. It's define at, was the person saying.
We talked about this. I know we spent probably an hour talking about, half hour talking about how can we get around it. It all comes down to verifying and validating that the person that is actually voting is actually a member. Who says it's not the 4-year-old that got the mail? And open up the envelope and triple stuff on, put it back in that self-addressed envelope, send it back, and that should be the qualifying individual on that.
That should be the qualifying individual in that family? I don't think so.
Well, so I mean, that's where we come in is who's the member? Well, who's the member of the house? Family. It's all, we have to do it right today so that if somebody challenges in the future, throws it all out, then that's a problem. I mean, I just had a dinner tonight that, well, for the last however many years, we never had a forum at our business meetings that were up to the board. So we're going to validate all those years that we had, didn't have a forum. I mean, if somebody really wants to challenge it, quite a while. And that's what we're trying to do tonight. I don't know how close we are. I know, was there 40 in the room? Steve, hey, Trina, what's the latest count? Oh, I think it's about 42. Yeah, so we have 120. 44 is here. 144. So, or 124. Okay, go ahead.
This is only a little facetious, but define a meeting. Why don't we say that a meeting lasts a month? We don't log out of this meeting. It just continues. Well, who says that we have to? I mean, if you can be online, if you can vote online, yeah. I mean, it's gaming it. I won't argue that, but
if we game it and nobody challenges it, are we cool? I don't know. We're really trying to keep this in the up and up, guys. Okay. So,
and how long would somebody have to challenge it? If they're challenging next week, okay, fine. But 5 years from now, would that even fly?
proxy votes are not allowed. I don't think they're allowed in the old one either. We can certainly look into this and see if there's some how should I put it, creative way that we can accomplish this. But we knew from the very beginning that getting a quorum was going to be the challenge. We knew that.
Have you ever gotten a 20%?
Okay, hang on a second.
So if there's always going to be an issue with having a quorum, can't we put into the bylaws that voting doesn't have to be at a meeting? Like if we're going to change the bylaws now to make it easier to vote, why don't we add that change that the voting can be done via the mail or online polls or whatever?
Yeah, we could do that, I guess.
But you're also changing it so it's 10%, so it's not going to be nearly the problem in the future. And as the current slide states, I think ethically, we have to abide by the current bylaws. Now, if we can find a way that's legitimate to get us through this, that's fine. But I agree with some of the statements already made. I don't think we should get cute and actually willingly defy the intention of the old bylaws. Otherwise, people are going to do it to this set too.
So Heather was talking about for the future, allowing other ways of voting.
I understand, but if we're going to 10% as the quorum,
right,
that's not going to be nearly the issue it is right now.
We easily at 10% tonight, easily.
Yeah,
Yeah, but barely.
Yeah, I mean, even at 1,000 members, we need 100. We met that tonight. We have 100 tonight. So I believe changing it to 10% is the right thing to do, and I also believe that we got to have some sort of representative number here. Could change it to 2 people, right? But that's not really a representative number. So
I think we should move on.
yeah, we're gonna have to move on.
So what we'll do is so the online people, the poll is open. You can launch, you can vote, and everybody in here has a ballot. And if and when we go and check the poll later tonight, if we have enough, we'll let you know. Otherwise,
We couldn't hear that.
Yeah. It was hard to hear what Mark was saying.
Test. Ooh.
I turned you up.
All right. Now you can hear me online. All right. All right. So we'll do this all over again in July. Like I was saying before I found out my mic wasn't working, is we're going to leave the polling. The polling online is up. It's running. It's launched. Go ahead and vote if you're online. Hopefully the people that come on late, if they do, they'll vote too, and we'll sift through it. And I still, it's not 9 o'clock yet, so I'm urging you to go and call your friends, email, text, whatever, get people to come on. Because I believe we're like 10 short, 15 short at the most. That would get us close. So there's a polling tool in your toolbox. If you get your toolbox to come up, it'll say polls in the middle. If you click on that, then you should see a screen come up. You should be able to pop in whatever vote you want there. And your choice will remain anonymous. I think
how do you get that box to come up again?
You should move your mouse to the bottom or wherever you see a little green. Who's online? I'm not.
My green thing says share screen.
Yep. So when you go to the left of that, a screen should pop up and you should see polls. Polls.
Not mine.
Yeah,
I had it on mine.
You had to register to be online.
Well, I registered when I signed on, I think.
Yep, you're right. So you can't see, unmute and start your video and all that.
I see mute, start your video, participants, chat, share screen, record, and reactions.
Matt, is the poll still on?
I think I voted, and I think after I voted, it disappeared. Is that true for
How
anyone
many
else?
people have voted? So 62 people have voted.
Yeah, that's what happened to me. After I voted, my poll icon went away.
Right, because it won't let you vote twice and it won't let you change your vote.
Right, so
Okay,
you
well,
could have
I did-
accidentally voted and clicked it off somehow, maybe.
There was a ballot up there when you said, take that thing off the screen, and I voted right then and it went off, so I wasn't sure they were related or what.
Yep,
That's
that
why.
got counted then. That got counted.
Okay, good.
All right.
Yeah,
thank you.
I just did a test on my system, and as soon as I clicked on submit on the poll, the option for polling in the toolbar at the bottom went away.
Yep, it should have. Okay,
I
enough
think
of that.
mine had a hanging shed.
So if we succeed tonight, we will give away all the prizes on this screen. If we do not succeed, I'll bring the prize package box back in July and we'll do this again. But as you can see, there was some anonymous donors that gave us money and we bought gift certificates from High Point and Cloudbreak Optics. Masters of Pix Insight, which is an imaging software processing tool. They so generously donated 10 coupons for future workshops that they have. And they also run a thing for an annual subscription for videos and information about running Pix Insight. They gave us 2 coupons for a 1-year subscription for that. Both of those are worth $100 each. The coupons for the workshop are worth $35 each. And Simulation Curriculum has donated two of each. Sky Safari 7 for iOS, Sky Safari 6 for Android, and 2 full-blown, whatever version you want, Sky Safari 8. Starry Nights 8, I'm sorry. So I thought that was very generous of them. And then beyond that, they even gave us a coupon 50% off for everyone. Next meeting is going to be here again, same way, except maybe with a couple less technical issues. We still have our Slack tool running. It's working great. MAS is on YouTube. There's that tiny little URL, and that will show up in the recording. You can always go get that later. Loaner Scope program. Anton, real quick, real short. That's not on. Oh, that microphone is off. Oh, no, we don't have 33.
Okay. Yes, as always, members can borrow our telescopes or our DVD great courses through the website under membership and Loaner Scope program. But since Mark told me to keep it short, I do have one important announcement. It's posted on the forum, and I'll just read it to you. Loaner Scopes will not be available from June 19th through July 4th. Members who want to use a telescope during this period must make a request and check out the telescope if available no later than June 18th. The program will resume on July 5th. As always, make requests on the forum found on the membership Loaner Scope program on our website. If the telescope is available, we'll schedule a meeting at my home before the deadline to check it out. Okay.
Thank you, Anton. Have a nice vacation.
Thank you.
He didn't say that.
Hey, question for you. Mark?
Yes.
The screen shows 80 participants. Did you get 80 votes from Zoom?
I don't know what we got. Steve and Trina went through that, and the official count of attendees tonight was 115.
Okay, so that's the online and in person.
That's correct.
Okay, and how many did you need?
133.
Oh, boy.
Well, 132.2. Okay, COVID, masks are welcome in here and in all MAS buildings and observatories. But I feel the most important part is if you're feeling ill or been around somebody that's ill, please stay home. And I apologize for last month. I had COVID last month and I didn't know it. I didn't find out till Friday when I tested after the meeting that I had tested positive. We did notify everybody to let you know so that you could watch yourself. I apologize for that. I had no symptoms. I felt fine. On Friday, I went over to my son's and I worked all day, pushing dirt, hauling boards around, all kinds of stuff. I put in a full day over there. I came home and I was fine. I just had a runny nose and, you know, I felt tired and my wife says, oh, maybe we better just do a test. Well, Friday night I was positive and, you know, I built a retaining wall on Saturday after that. I mean, I'm just saying I didn't have anything. So if anybody got sick, I apologize for that because it was probably me. And I still have no idea where I got it. So here's a list of events that are going to happen before the next meeting. The most exciting one on there for me is the summer solstice because that means nighttime is going to start growing. And I realize not very fast, but it's not going to be getting any shorter. That's the cool part. And then I was kind of interested, you know, Earth at aphelion on July 4th, you know, farthest from the sun, but it's July and I bet it'll be 85 that day. Things that are going on as far as public events and member events before our next meeting. Star Party at Eagle Lake on this coming Saturday. The BSIG at Metcalf Field as June 11th is the primary and July 10th or June 10th is the backup. And then the only other plug I have is the astrophotography meeting is at ELO. That's a rain or shine event. And then Star Party again on June 18th at Eagle Lake. I suppose they start looking at telescopes about 10:30. It gets dark now. But I've been told, Merle's told me 1,000 times, there's plenty of things to look at even when the sun is up. Right, Merle? Get the okay signal from him. And then CGO is open every day for members. And then you see there the 3 events at Long Lake Conservancy Center. And I better get going. Again, the special interest group has an event on June 11th with Friday as the backup. If the forecast says that Saturday night is going to be cloudy, then and Friday night is clear, they would just have the event then on Friday night, and they start at 10. And watch the forums, your email, and the website for changes. Other upcoming events, we have our partner, Long Lake Conservancy, LLCC. They have an astronomy camp August 3rd through the 7th. They have the teaching part and all the other stuff pretty much handled from what I understand, but they certainly would enjoy having us, MAS members, maybe open up our stuff if it's clear during that week and show the campers some things and maybe take up some telescopes and kind of just hang out with them and kind of help them bring the laboratory to the classroom, so to speak, by after the sun goes down, you know, here's all the wonderful things we were talking about in class. And I imagine they'll have some solar viewing and things like that too during that time. And then Camping with the Stars is coming up. Wow, where did the summer go? What are we talking about the end of July? I'm sure Merle is looking for volunteers. I'm sure he is looking for speakers. So if you're interested to have a presentation, something, certainly could get a hold of Merle or Lila. Anything else, Merle? Not right now. Stay tuned for July. The July meeting will have some more details. Question, Dean. Gemini. The Gemini editors are always looking for articles. So if you've been somewhere cool, done something cool, bought some crazy piece of equipment that is a lot of fun that you'd like to share, certainly write an article and submit that to Father Brown. And the rest of us will enjoy it after that. Thank you. Better Know a Constellation is going to be presented tonight by Claire Skies Weaverly.
Nice.
The most adorable constellation in the night sky. And Claire, I guess I have your slideshow, so I will, I'll just run it from here.
Okay, all right. Hello, everyone. I meant to be there in person and that didn't happen. So sorry about that. I know sometimes it's hard to find recruits to do Better Know a Constellation each month, and I didn't mean to volunteer myself, but I think I made one too many jokes about Delphinus and how cute and adorable it is, and somehow that volunteered me to do a presentation on this constellation. So here we are. Most adorable constellation in the night sky. Why is Delphinus so adorable? Next slide. Well, it is one of the smallest constellations, coming in at 69th of 88 constellations. And it's meant to represent a dolphin jumping out of the water. So there's the 5 stars that make up the dolphin. And this originates, as with many constellations, in a Greek story. So this was one of the original Greek constellations cataloged by Ptolemy. And there's 2 different stories actually explaining how this got into our night sky. I'm not going to tell both stories. I'll just tell one of the stories. So there was a poet named Arion from Lesbos, who was both a poet and court musician at the palace of the ruler of Corinth. And he went traveling and participated in a singing competition and amassed a fortune in doing so, and was traveling home with his great wealth. And the sailors aboard the ship became covetous of this and plotted to either kill him or have him commit suicide and steal his wealth. And so he pleaded with them to have one last wish to be able to sing a song before dying. So he sang a song and threw himself over the side of the ship. His music was so beautiful that the dolphins congregated around the ship, and when he threw himself into the water, one of the dolphins took pity on him and saved him and brought him ashore. There's lots more to the story, I think, than that, including that the dolphin, I think, died and was made into a monument or something like that. But long story short, Apollo, the god, put the dolphin in the sky in gratitude for the fact that the dolphin had saved the poet who served the god Apollo. So that's how we ended up with a dolphin in our sky. If you look at the 4 stars at the top of the constellation, that is also an asterism that's sometimes referred to as Job's coffin. I'm not actually sure. Yes, Apollo, god of music. So I'm not actually sure how Job's coffin, how that came about, but I'm assuming it was Job from the Bible, and then the smushed rectangle looks like a coffin. All right, next slide. All right, so how do you find Delphinus? Very easy to find. It's near the Summer Triangle. So most of you, I'm sure, are familiar with Deneb, Vega, and Altair. So if you look just off of Altair, there you'll find what actually, to me, in addition to looking like a dolphin, looks like a small kite with a little tail. And so obviously you can see this throughout the summer, but actually prime viewing for Delphinus would be September around 9 p.m. And so next slide. All right, the 5 stars that make up Delphinus, there are some interesting naming conventions we have going on in this constellation. So both Alpha and Beta stars are binary stars. Alpha is a binary that also has 5 faint other stars in a system with it. So those stars together make up a 3.8 magnitude star from our vantage point. And then the Beta star is also a binary, and that is a 3.6 magnitude star. That is the brightest one in the constellation. But interesting story about the names. The official names of these constellations are Sualisin and Rotanov. And for the longest time, it was very mysterious about where these odd names came from. And there was a British astronomer named Thomas Webb who finally figured out this mystery. So if you go back to 1814, those names first appeared in a catalog put out by the Palermo Observatory in Italy. And he figured out that the assistant astronomer at the observatory, Niccolo Cacciatore, if you translate his name into English, it's Nicholas Hunter. And then if you Latinize that name as Nicholas Venator, and then you spell that backwards, that gives you the names of the stars. So obviously somebody at that observatory had a good sense of humor. All right, next slide. The gamma star is also a celebrated binary star. I think mostly because of the interesting color combinations of the orange gold star along with the lime green star that together looks quite lovely. So that might be an interesting object for people trying to separate binaries. And then another cute name, the tail of the star Epsilon Delphini is also in Arabic Deneb Dolphim or Aldufin, which translates as the tail of the dolphin. And next slide. Okay, going back to the comment that Apollo is the god of music and the story about Arion, who was the poet who served him. So there are 5 stars in Delphinus where scientists have discovered exoplanets around the star. 18 Delphini is an example of that. They did find a very dense, massive planet orbiting that star that's 10.3 times the mass of Jupiter. And as part of the Name Exoworlds competition, a group of students in Japan who were part of a science club got to actually pick the names. So they got to name the star Musica, which is Latin for music. And then the planet is Arion, named after the poet who won over the dolphins with his music. All right, next slide. This part of the sky is also a great hunting ground for supernova. I came across at least 3 supernovas that occurred. There's probably more. I'm just pointing out 2 of them, 1967. And the interesting thing about the one in 2013, B339 Delphini, was that it was discovered by an amateur astronomer, Koichi Itagaki, and it was the first nova where scientists were able to observe the nova actually synthesizing lithium. And apparently they're not able to observe the lithium within the nebula, but when it's ejected from the nebula as part of the wind, they were able to observe the lithium. And next slide. Right, there are no Messier objects in Delphini, but there are some interesting deep sky objects if you've done Caldwell or if you've done the Globular Observing Program as part of the Astronomical League. This is a good comparison. The Shapley-Sawyer spectrum, where you have really dense compact globulars at one end of the spectrum, and then a little bit looser globulars or much looser globulars at the other end of the spectrum. This gives you the contrast. 7006 is actually a 1 on that spectrum, so very dense globular, and the other one is very loose. So that would make an interesting observing challenge. Next slide. There are also 2 planetaries, the Blue Flash, and then this other really interesting one, 6891, which is super interesting because there's a lot of interesting structure going on inside the nebula, resulting from the fact that this is a result of different outbursts that occurred at different times. So for example, the outer halo is expanding faster than the inner halo, and the inner shell is about 4,800 years old, whereas the outer part is almost 30,000 years old. So there's lots of super interesting structure inside that. Next slide. There are a few galaxies there. I have not observed 7003, but I recently started the open cluster list, And as part of that, I actually wasn't intending to observe 7025. I was looking for the toadstool, but it just happens to be right off of that galaxy. And so that was really interesting to see both the open cluster and the galaxy together. And that open cluster, the toadstool, is actually French 1. And in keeping with our theme tonight, it's also adorable. And so that is Delphina, or Delphina.
Thank you, Claire. And I just want to remind all members that are on this call and in this room that we're always looking for somebody to do that presentation. Jerry Jones carried the cup of that water for quite a while. He took the month off, only because I didn't ask him, because I knew Claire was working on something. That'd be Claire Skies, by the way.
That's the name of my scope, not my name.
Yeah, well,
FYI.
I'm using that as your nickname from now on. Thank you, Claire.
You're welcome.
Moving along, no Astronomy League awards this month, but Jerry always has the get out and observe mantra he carries along with his cup of water. Next month, Bob King will be here, and his topic will be anything but meteorites. So looking forward to that talk. And tonight we have the pleasure of Professor Larry Rudnick in the house to present to us a topic of a square meter of collecting area, early ESCA Pathfinder. Square kilometer, what did I say? So it's a little bigger. So let's see, does this work? This works. This works. Look it, Larry's in the house. You know what? Ahmed called me today, and he let me know that the last meeting that we had before we shut down, before COVID, Larry was here. And the first meeting that we've had where we've had a live in-person speaker, he didn't go away. He's back.
I was thinking about it.
He can't vote, but we could sign him up. You got $40?
You're gonna give me a check, right? Or turn it back over.
That'd be kind of cool.
It's always a pleasure to speak with this group. You guys are easy to speak to because you're going to be interested in anything. It's got pictures and stuff. But before I came tonight, I was talking with my wife, and we were arguing about whether you guys all had your head in the stars. So I have a quiz for you. It's a news quiz. Which of the following metals were in the news today? A, was it titanium? B, was it platinum? C, was it palladium? D, none of the above. Okay, so we're going to have a show of hands. I can't figure out what's going on online. A, titanium. B, platinum. Oh, a few votes for platinum. C, palladium. D, none of the above. Somebody that knows the answer, yell it out, please. And it's platinum because it's the Queen's Platinum Jubilee. Okay. So when I started doing interferometry many decades ago, in the late 70s, at Green Bank, we had 3 telescopes. The way interferometry works, whether it's radio, which is the standard, or optical, it depends on pairs of telescopes to create interference fringes. And so the signals that you get, the amount of information you get depends on the square, n times n minus 1, actually, of the number of telescopes. So with 3 telescopes, you get 6 pairs. And that's what we did. And you get 6 tiny little pieces of information. You can't make an image out of 6 pieces of information. So what we did was, I was living in Charlottesville at the time, in Virginia, across the mountains from Green Bank, where the telescopes were. And you would travel over, and you drive over the hills, take several hours and stuff, and you would go look
and you'd get 6 data points. And then you drive back. And then they would move the antennas. And a couple months later, you go and you get 6 more data points. And after doing this for years, you could make an image. That was 3 telescopes. And then 40 years ago, because we just had a meeting commemorating the 40th anniversary of the Very Large Array, which is where I spent, where most of my research for most of my career was, we had 27 antennas. And that was 351 baselines. I'm sorry, it's n times n minus 1 over 2, but we had 2 receivers on each, so we had 6 pieces, whatever. 351 or 702 pieces of information that would come in at a time. And people envisioned that we could do bigger and better than that, and they started talking about the square kilometer array. And that is actually having a square kilometer of collecting area, just enormous, spread out over some enormous plains or whatever, and broken into thousands, hundreds and thousands of pieces, hundreds and thousands of individual antennas that could be put together, give you basically the Fourier transform of what's going on in the sky, and then you would invert that Fourier transform and make the image. And we're on the way. The SKA, which the US is not an official member of, although we are a partner in contributing various types of things, we're not officially a partner of the Square Kilometer Array, which is what SKA stands for. But there were 2 countries that bought into this big time, Australia and South Africa. And they made national level investments and said they were in competition essentially with each other. We want to host this next generation thing. I don't remember the exact date for completion of the first phase. It's somewhere in the early 2030s or so. But on the way there, we had a lot of technology to learn. And so both Australia and South Africa built what they called Pathfinder telescopes. The Pathfinder telescopes were meant to test the technology, to get all of these antennas working together, to get the software, to get the computer systems. And believe me, there were plenty of things to learn. And so I've been heavily involved. I retired actually 2 years ago. And I've never had so much fun in my life because it gave me much more time to do research, which I'm doing, and not doing the things like grant writing, which I hated doing. I was able to get involved in these major projects, the Pathfinder projects in Australia and South Africa. And in Australia, it's 36 antennas. I haven't even done the multiplication to figure out how many baselines, how many data points you could get at once. And 64 antennas in South Africa. The array is called Meerkat. And it's you're going to see where they are and stuff. The change in the amount of data from 3 antennas to 64 antennas is just mind-boggling. And what you do, and we did even with the 3, and you do with the 36 or the 64, is what we call Earth rotation aperture synthesis. You take the data and then you let the Earth rotate a little bit, and you get new data points. Rotates a little bit more, you get new data points. Sometimes you go off and do something in between because you don't have to really do it continuously. But if you really want high quality maps, high dynamic range, you need to keep everything tightly under control. So typically we'll observe for 8 or 10 hours or something like that, and you'll track the position in the sky, and you get many millions of data points. And the quality of the images and what we've been able to see, even so far with the Pathfinders, is just spectacular. And that's what I'm going to give you a little flavor of tonight. So I'm going to show you the results from these two Pathfinder telescopes. Eventually, when the competition and the international organization had to figure out where they were going to build these arrays, the answer is they're building it in 2 pieces. One piece in South Africa and one piece in Australia. One of them, the Australians will have a low frequency array. The South Africans will have a higher frequency array. So on the path to the square kilometer array, you see in the bottom right here, the maps of South Africa and Australia and the location of these arrays. The scale is just mind-boggling. I mean, these are spread out over these very large swaths of desert. And I haven't been to either site yet. I mean, this has happened during COVID. I haven't been either to the headquarters or to the site. I was head of the technical working group for one of the surveys that was conducted on these, but it was all remote. It felt like, well, I need to go there and at least touch the antennas or touch the receivers or something, but I haven't been able to do that yet. So these are the combination of artist conceptions plus real pictures of the pathfinders, which are these early pieces of the telescopes. So on the left, you see a picture of the high frequency antennas. Those are kind of standard dishes, standard radio telescopes with the receivers at the prime focus. And usually a series of receivers there so that you can work at different frequencies and switch to different frequencies. And on the right, you see the low frequency array, and those are bizarre looking things. I mean, those are like radio amateur antennas, little folded dipoles with ground screens and stuff. And just the beams are very big, but you combine them all together. You can point them and get very high resolution. In the Netherlands, there is an array similar to this, the low frequency array LOFAR, that's been getting spectacular results as well. So this is just a quick slide to show how dramatically things have been changing. This is a log plot, logarithmic plot of the number of sources that radio astronomers have detected from the earliest days. So the radio astronomy basically started with Grote Reber, basically in his backyard, playing with Bell Labs old telescope, and there was just a handful of sources. The first big surveys were done in Cambridge, England, and there was a few hundred sources in the sky that you could see that were strong enough to be able to be detected. And today, over on the right, is the current surveys that are going on, and we're pushing 50 million or so sources, which creates all different kinds of problems. When you're trying to catalog them, when you're trying to describe them, when you're trying to study morphologies, when you're trying to figure out what it is that you're looking at. And I'm involved with a number of sort of new ways of looking, whether it's machine language looking or citizen science, stuff that we've done on Zooniverse with Radio Galaxy Zoo that was actually the topic of one of my earlier talks here, these tens of millions of sources that we have to deal with. The Square Kilometer Array went out with a series of goals. One major goal was to do cosmology, to study the evolution of the universe. You can see back to the earliest times with radio sources, to study their evolution over time, to study where my study is in clusters of galaxies and radio galaxies, to figure out the roles of dark energy, for example. So that kind of cosmic, very large scale stuff. There are completely parallel programs that people are interested in studying, in using pulsars to test gravity. So pulsars, of course, are very precise clocks, and we've used them and we do all kinds of interesting timing experiments with them, but take a pulsar and put it near a black hole and the game changes, because the black hole changes the nature of space and time in the vicinity of the pulsar. And so the pulses come through this gravitational field in which time and space is distorted, and the timing of the pulses as they come in is distorted. And you can test how well your theories of gravity are doing by watching as the pulsar orbits in and out closer and further away from a black hole. So another whole area for the SKA. Cosmic magnetism. Magnetic fields are so important in many different areas of astronomy. One of them even being how stars form, that magnetic fields play a large role in either channeling material in to help stars form, or more commonly to prevent the collapse of clouds, providing some pressure and keeping clouds from collapsing into stars. Very complicated roles. We know that the magnetic fields are important because we see the stars with the magnetic fields. As they collapse, they carry the magnetic fields in with them. And we can see those remnants today. But how those magnetic fields first developed in the universe, how did they build up from the very origins, and there's a variety of different theories, to the amplification. We know, for example, that there are things we call dynamos that amplify the magnetic field in the Earth and the other planets. There are dynamos on much larger scales as well, and other mechanisms to amplify the magnetic fields up to the levels that we see today. All the maps that I show you in the radio, they basically are synchrotron radiation, which depends on magnetic fields. So we know these things are everywhere, and that's another big challenge, project area for the SKA. Finding the first stars, the first black holes and quasars that formed, another major area. Looking for life on other planets. So ALMA, the telescope in Chile that works in the millimeter and submillimeter part of the regime, we know there's been fantastic discoveries about early solar systems on things. The SKA is also going to be playing a major role. It will likely be involved in some of these exoplanet observations. Once we can start doing absorption experiments through the atmospheres, we're going to get all kinds of information. I mean, the SKA complementing lots of other information. And then finally, whenever you put some major new technology out there, the most exciting things are going to be the things that you can't predict. And so there's an importance to understanding that. My colleagues wanted to call this the WTF, and you can do the translation yourself, side of the science, and the journals wouldn't accept it. So you're going to see. I'll show you one quick example of one of the new class of objects. But the question is, if you know beforehand, which we do, that the most exciting things are going to be the things you can't predict, what do you do about that? And what you do about that is you make sure that at every step of what you're doing, you stay flexible, so that somebody that recognizes something new or has some new idea doesn't have to follow exactly the same path as before. Has flexibility with the software, flexibility with the electronics, flexibility with the observing schemes. You build as much flexibility as you can, and there's a tension because flexibility usually comes at the expense of efficiency. So you've got to trade off your efficiency against your flexibility, but we know that this area is extremely important. And so we try to build in as much flexibility as we can. And interestingly enough, even the machines, which you might consider the most mechanical aspect of things, giving things to a computer, computers now are not doing what you tell them to do. They are making the rules up themselves. That's what artificial intelligence is. And so we're giving the computer these images. And one of the things, one of my colleagues in South Africa has developed a software system called Astronomaly. And she takes images, thousands, tens of thousands of images, runs them through, and then gives you the list of the most anomalous ones, the things that don't look like the other things. And then you go look at them and you go, is there something new that I can learn from these? Okay, so the two pathfinders, the Australian SKA Pathfinder, which goes under the acronym ASCAP out in Western Australia. And here's a couple of things that have been studied there. One is fast radio bursts, and the burst that I'm showing you here is not the one discovered at ASCAP, but the these are intense bursts. We don't know their source yet. We don't know what's causing them. Interestingly enough, I was looking for these for my thesis in 1973. I didn't detect anything. I didn't even publish. Oh, it's very embarrassing. It doesn't matter. I was just 30 years ahead of my time or whatever. We're sensitive enough now that we can see these bursts, and we don't know what's causing them. That's what's exciting. What ASCAP has done is been able to take deep images and find the galaxy in which some of these bursts were located. And that's a start, because when all you have is a burst of radiation, you don't even know how far away it is. So you have to find the host, you have to find where it belongs. And that's one of the things that the ASCAP telescope has done. This is what a survey looks like. So you can consider this something like any survey that you know of an area of the sky. This is 36 square degrees. This is a field, 36 square degrees. And you make an image, it takes about 10 hours or so of observation, and you make that image. We did a pilot survey using ASCAP so that we could test the methods, we could see what the sky looked like, we could see how our processing schemes were going to work. And I'm just going to zoom you in a little bit on this one area in this box here. So we zoom into the box. Most of the sources you see here are background sources that are far enough away that they just appear to be points. Virtually none of them are points. Some of them are individual active galactic nuclei, black holes on scales of maybe a couple of parsecs or something like that. That's a minority of the things in here. So some of them really are small, but most of them are things that are probably about the size of our Milky Way, maybe 10 kiloparsecs or something like that, but so far away that they, even with a high resolution, we're talking about 15 arc seconds. It's not optical resolution, 15 arc seconds or so resolution for here. And then there are some giant radio galaxies in there, and you can see one in the box and another one near it. So in the core, in the little bright spot, and you're going to see it in a minute, is where the active galactic nucleus sits. And then there are jets of material which are spewed out over hundreds of thousands of parsecs, hundreds of kiloparsecs, sometimes even out to megaparsecs, so a few million light years across. Enormous amounts of energy channeled into these jets. And that's part of what I study is how did these jets get collimated? How did they get so much energy pumped into them? What happens to them when they interact with the medium around them? And that's actually most of what I've done in my career, and new things are just completely opening up now because of that image. So we're going to zoom in further. We're in a small patch now of this 36 square degrees, and this is a picture of that that radio galaxy. This one is a few hundred thousand parsecs, so a million light years across or so. And how does it stay energized? Where the particles are radiating away their energy, how do you keep pumping energy into them so that you can continue to see it? And I don't know if that's the last, yeah, that was the last zoom. So let me just point out that if you look carefully, and the room's a little bit light for this, but there are lots and lots of faint things that, yeah, if we could just take the light, if somebody could grab and get the lights down a little bit, you can see that as just like the stars, as you go fainter and fainter, there are more and more objects. So I just wanted you to see how many there were in, that's good, great, thanks, Mark. So you get a sense, I mean, this is what builds up to 20 million. And some tiny fraction of them will be big and interesting, and most of them will just be small, and we'll measure a few properties of them. We'll measure their spectral distribution, we'll measure their polarization, but the detailed mapping projects will be a tiny fraction. So I'm just going to show you again just a couple little things. The source on the right, let's just look at the one on the right here. People are calling this the dancing ghosts. And actually, is there a pointer here on here? Yeah, There we go. Okay, so you guys at home are not going to be able to see this, but if you look at the picture on the right, we're looking at a radio image in this kind of light cyan color and an optical image on which in white on which it's overlaid. And there are apparently two radio galaxies here, one here that shot out jets. So that's at the top, shooting jets out to the left and right. And then another one here, which is again shot out jets. We don't understand how this structure formed. It could be a complete random superposition. And you could say, well, that's too much of a coincidence. But the answer is you can't dismiss coincidences that easily when you're looking at very large areas of the sky. Because if you're looking at thousands and tens of thousands of sources and picking out the most interesting ones, you could get fooled and you could be picking out coincidences. So that's a difficult part of the business. If these things are interacting with each other, we've got a great new physics laboratory. Because if these jets of material are bumping into each other and interacting and twisting each other around, fantastic. We will learn a lot about them. But if it's just a coincidence, we have nothing to learn. And the question is, how are we going to decide? And we don't know yet how to do this. We can estimate what the chances of seeing it is, but it's really hard, again, because you're looking for odd things. Sure enough, you find them. We don't know how to make this kind of source. This was the object that my colleague wanted to call a WTF. And what we had to, in the end, call it was an odd radio circle. And the original image, you can see in the pictures on the left, that was made with the ASCAP telescope in Australia. The one on the right was made with the Meerkat telescope in South Africa, which has better resolution. And a talented colleague who knows how to do all these colors and stuff made this beautiful image. We don't know that this was a new type of source. We had never seen this kind of source before. When the first time we looked at it, we said, oh, that just looks like a planetary nebula or looks like a supernova remnant. We know those things, but this is not. This is associated with a very distant galaxy. This is, again, hundreds of thousands of light years across. And how do you make these circles? Are we looking at two cylinders kind of edge on? Are we looking at two spheres and just sort of seeing, the edges of them? Or was this a spherical explosion that ended up getting a little asymmetric because the environment was different on the two sides? We don't know yet. The images on the left at the bottom are the ones I made, so I stuck them there. They're not as pretty, but they're just as important. I was studying the spectral distribution and adding that and adding the polarization. So we know, for example, that the magnetic field goes around the edges of this thing, which kind of suggests maybe an explosive origin, because that's what would happen in an explosion. You would sweep up the magnetic field along the edges. We've now got about 10 of these. So there's this whole class of odd radio circles, and eventually they will get other names once we figure out what they actually are. But right now, we just don't know. We're studying clusters of galaxies. One of the amazing things with all of these telescopes, when you get them close together, then they form a large beam on the sky, and you can be sensitive to very low surface brightness stuff. When you take them far apart, they put a very small beam on the sky, and you're sensitive to more, higher structure sources. And there's so many of these telescopes now that we put some of them close together and some of them far apart, so you can play both games at once. And so on the left is a cluster of galaxies, which is one of the things that I've studied. And the red region and the contours which are there were very low surface brightness stuff, which we were able to separate out from all those other little point sources that you saw in the images. You have to get them out, filter them out, and then you can look for this low surface brightness stuff. So this is one of the things we're looking at. In the clusters of galaxies, we are looking at a relativistic plasma, which is what's giving us the radiation, coupled to another plasma, which we call thermal plasma, which is just hot gas, but it's very hot. It's 10 million, 100 million degrees radiates in the X-rays. So you take an X-ray picture and you see a glowing plasma there. You take a radio picture and you see a glowing plasma, if you will. One of them from relativistic particles traveling near the speed of light, giving you synchrotron radiation. One of them just thermal radiation from gas, which really is physically at 10 to 100 million Kelvin. And the interactions between those two, fascinating area, it's what kept me awake at night for a long time, is figuring out how these two couple to each other, how motions in one affect motions in the other, how energy gets transported back and forth. Those are the kinds of things that I've been working on. Here's a closer look at Meerkat. Let me just check, is Mark, where'd Mark go? We lost Mark. Somebody tell, is 9 o'clock a hard cutoff? They're going to throw us out? Okay, so if I start going over my welcome and you start drifting out, I'll know. But as long as they're not going to come and throw us out of the building. So this is the Meerkat telescope, and you can see what I was talking about here a little bit. If you look at the configuration of the telescopes, there's a group of them in the center that are close together. That's to give us the sensitivity to this very large, low brightness diffuse stuff. And then there's a bunch that are further apart, and they give you the very pretty maps of all the little points and stuff. And you can see where this is located in South Africa. Yeah. Yeah, yes, but it's a deliberate random. Yeah, it's a tailored random. So what we do for anybody that, you know, it's how to best say it. If you took one of your mirrors or a lens and put lots of little black tape, I mean, it's horrible. Why would you ever put bunches of little black tape over the mirror? You're still going to get an image, but it's going to have distortions in it. It's going to have side lobes, it's going to have diffraction spikes, it's going to have stuff like that. We carefully randomize things so that it's not too bad and that we get this high and low surface brightness sensitivity, but not too bad on all the spikes and everything. They cancel each other out and then they get canceled out again because you do the Earth rotation stuff. But you're right, it's semi-random, but tailored to make a cleaner image. Yes, a regular pattern is bad. We built telescopes like that, and you get interference fringes that coherently add up. And so what you think is just a point source will give you something like an airy pattern, but it's a bunch of them that are all going to add up on each other and give you these giant rings. And you go, where's the real emission coming from? And so, yes, regular turns out. There are some advantages, and there's the telescope that the Dutch built in Westerbork many years ago had regular spacings, but they also were responsible for LOFAR, and that is much more randomized. So here's an image of one of the clusters that I worked on from the Meerkat survey. The numbers are not going to mean anything. Most of the numbers are not going to really mean anything to you, but the field of view now, single snapshot, 2 degrees by 2 degrees. That's because they built small dishes. So the small dishes give you a large field of view. You build too big a dish, you can only see a small area of the sky. So they decided to build lots and lots, 64, of 13-meter dishes, which is rather small for a radio telescope size, which gives you a large area of the sky at once, so you can see 2 square degrees. It's the thing you want to do for surveys. If you want to survey the whole sky, you want your snapshots to be pretty big. ASCAP made a set of different choices, and anybody that's interested in the technology of phased array feeds, which is what they use, they had another way around it. But basically, you have to design something that can take pictures of large areas of the sky if you intend to do the whole sky, which is what these things do. So Meerkat, it's actually not clear that it will ever do the whole sky. Maybe it will. The SKA will have enough antennas. It will be able to do the whole sky. But these projects will take years to just map the sky once. And then you go back and find the interesting things and spend more time on them. So on the left was an image that I made for a paper that we put out on some of the meerkat observations. And I'm pretty proud of that image. And so I just want to show you what it was. On the left, in the triplet, what's the word? Triptych. In the triptych on the left, there are 3 images there. The one on the far left is the original image from the meerkat survey. So that's the sky as it looks to the radio telescope. And if you look carefully, you can see there's some fuzzy low brightness stuff in the center. So if you want to detect that low surface brightness stuff, what you can do is you can smooth your image. And that's what we do. We convolve it down, we smooth the image, and that helps add up the signal when it's spread over a large area. And that's what the middle image is. But what happens is that all those little points there also get smeared. And now in that middle image, we reach what astronomers call the confusion limit. And what we mean by that, that's a cute term, but confusion is a technical term that we use. And the technical term means basically that at every position that you look in the sky, there is at least one and sometimes several objects. Every position, there's no dark sky. There's no black. Everything, every place you look has got signal in it. And when you're in that limit, you can't tell what you're looking at. You don't know what contributed to the brightness in there. So I want to detect this low surface brightness stuff. Yeah.
I think the people at home might not be able to hear as well.
Okay. Sure. So we're interested in pulling out the low surface brightness stuff. By smearing, you get into what we call a confusion limit. Radio astronomers many years ago built sensitive enough instruments to get us down to the confusion limit. So we had learned about it. We developed mathematics of it. We published papers on it. You know, when do you get into the confusion limit? What can you learn from it? What do you do about it? Things like that. We watched with some amusement as the X-ray astronomers rediscovered it. And you could see papers coming out and they were confused about what they were looking at and stuff. And we said, yeah, that's confusion. We've been there before. Once you get sensitive enough, every place you look has emission in it, and you have to have special ways of dealing with it. And so a number of years ago, I had written a routine, an algorithm, basically to get rid of all these little points in a very efficient way before you do the smearing. And that's what the image on the right is. So the image on the right is that very low, faint stuff that you can barely see on the left. And there it just pops out. And so for the survey that we did, we were able to pull out all kinds of emission by running this filtering technique, getting rid of the points, smearing things down after all the little stuff was gone, and finding these very low brightness areas. Another problem when you start getting this sensitive is that if you get a big source, big radio galaxy like the one on the right that we want to study, it's got interlopers. So all those little circles have nothing to do with the radio galaxy that we're looking at there. They are just background sources. And so again, we need techniques. We need new learning, because it used to be that our images were not deep enough that these things wouldn't be there. But now that we're making such deep images, when we look at large objects, we're covered with interlopers, and being able to separate out those interlopers. This is the kind of stuff that we're learning, because with the SKA, we're going to be hitting all of this. So this is what the Pathfinders were meant to do, to kind of find some of these problems. The image on the left is one of these where I filtered out all the small stuff and was able to find what previously was an extremely faint patches of emission, which here stick out like a sore thumb after I get rid of the point sources and smear them down. And they're a giant radio galaxy on the way out. So I've shown you examples of jets of material, for example, that were shooting out of the radio galaxies and filling these big, what we call lobes, big clouds of relativistic plasma that are shining. But then the jets turn off after some time, maybe after 10 million years or 100 million years, the active galactic nucleus stops sending these jets out, and the radio galaxies begin dying, fading away. And studying that process, again, is another interesting thing that we're after. And so you need to be able to go and see very faint stuff because you want to trace it as long as you can. You know, we're not seeing any of them fade. I mean, the time scale for fading is 100 million years, a billion years. But we're taking pictures of these very old systems where they're no longer being powered, and we're catching them in their fading phase. Giant shock waves. When clusters of galaxies, thousands of galaxies, 10 to the 14th, few times 10 to the 14th times the mass of the sun, amazing amounts of mass colliding with each other in space. These X-ray plasmas that I was talking about, forming these enormous collisions, creating shock waves and other various structures and strange flows during these cosmic collisions. Again, things that take place on billions of years, but we can see the shock waves. And sometimes we see them in the radio, as the pictures that you see here, and sometimes we see them in the X-ray. And that's another thing that we're studying in much more detail now with this new generation of telescopes. Yeah, I'm going to have to rephrase the question. Okay, so the radio galaxies that we are looking at and these clusters and everything else that I've been showing you is due to a population of relativistic electrons that spans many orders of magnitude in how much energy the particles have. The low energy particles radiate at low frequencies. The high energy particles radiate at high frequencies. We will typically make images at low frequencies and high frequencies to be able to determine how many low energy electrons are there compared to how many high energy electrons. And so that slope can change depending upon how these particles got accelerated. A bigger source will have more of them, so everything will just go up and get brighter. But there are really two different effects embodied in your question. What is it that determine the ratio of high to low? It's just like taking colors. If you take a red filter and a blue filter and you get a color index or something, you're looking at the emission at one band compared to the emission at others. For us, that's looking at low energy electrons and high energy electrons, and those ratios tell us about the acceleration process. It's not really temperature because they're not thermal. Yeah, it's not thermal. So I'm going to skip over this because we're closing up on 9 o'clock and I do want to leave time for questions because you guys always have good questions. And I'm just going to show you. So I had a whole team of people in the Galactic Cluster Legacy Survey from EarCat that were finding and sending me interesting things. And I got hundreds of suggestions of, here's an interesting object, look at this, and here's an interesting object, look at this. I had a lady doing the astronomy stuff. She sent me a number of the same ones that people were sending me. Her routines were picking out some of them. Out of those hundreds, I picked out a handful that I thought challenged our current scientific thinking. And so we published in the paper, and I'm not going to go through these, but a handful of these in which our current theories can't make them. So of course, nature made them. There's a way. It's just our theories today are inadequate to explain the structures we see. It's a difficult business because it's like looking at clouds. You look at some complicated clouds, it doesn't necessarily teach you anything. Well, the wind is blowing this way and that way. And so it made this funny structure that looks like apple pie, but you don't learn anything from it. And the challenge is, how do you pull out those that are so clear, but don't match the kinds of things that they look simple in some way, but they can't be explained by the theories that we currently have. And that's what we're starting to find, is all kinds of examples of those. And so I'm not going to go through them, but I will show you this gorgeous picture, because one of the things that's coming up is that we're finding filaments, very thin streams of emission. We're finding them inside these radio galaxies. We're finding them outside these radio galaxies. This is a phenomenon that was hinted at before, but until we got this high resolution, high sensitivity, ability to filter out confusing stuff, that we're now pulling out these filaments. And I have a 30-page paper, which is in refereeing now, and hopefully they won't give me a hard time, because we're kind of breaking new ground and trying to study these filaments. And ended up, I assembled a team, and we wrote up a lot of stuff about them, and hopefully the referee will like it. And one of the things that we did, and I'm just going to skip through a bunch of stuff here, is, and this is really cool, found a way to reconstruct the 3D structure in some limited circumstances. And so the object on the left is a radio galaxy, and it's got some streamers coming off to the north. And let's see if I get this. I developed a way to pull out some of the 3D structure, and there's a 3D image of that object, and it looks like twisted braids going around each other. And we'll see what the referee says about that. I presented this at a couple of meetings, and nobody has completely shot me down yet. There are some assumptions there. And this is another piece that we were able to see in 3D. And so that's something new that we're able to do with these telescopes. So this is a radio lobe that you can see again in the box on the left. And on the right, you can see it's a bunch of filaments that are in this kind of semi-spherical type pattern there. And then finally, this is some of those filaments that I was talking about. Yes. Yep. There probably is some vorticity going on. This, oh my God, this can keep you up at night. This is not, this was an astronomy picture of the day in February. The Galactic Center, Farhad Yousafzadeh at Northwestern University made this image. This is again made with Meerkat, one of the precursors, pathfinders. You're looking at a bunch of different things. Some of it is thermal emission. So despite the fact that I said we're looking at synchrotron emission, in the radio, you also can see thermal emission sometimes. And so the sort of orangey color stuff, I think, is more thermal, but it's a mixture of thermal and non-thermal. And there's these filaments in there, most of them vertical. And he just gave a very nice talk at a meeting that I was at, concentrating on magnetic fields, trying to speculate on what is causing these filaments, how are they being powered. And so this is a different scale than in the clusters of galaxies that I was looking at, but we have a lot to learn from each other because we're both seeing filamentary structures. And so I'm getting together with Farhad, and we're going to do some analysis on this. And so we're on our way to the square kilometer array. Whether I will still be mentally coherent by the time the data start coming in, I won't be writing proposals, that I know, but I hope at least that I'll be enjoying the images coming out of them. But in the meantime, we have these Pathfinder telescopes that are doing fantastic work, making all these discoveries and giving us a lot of pleasure. And that's it. Thank you. Yes, Dean, I expected no less. Oh.
Wait.
That's my mic.
Well, bring it back. Got to share, Larry. First of all, thanks. Every time you talk, I swear I get chills up and down my back, and it's just, and I grin from ear to ear most of the time. Two questions that occurred to me along the way. One was, as far as confusion goes, how many regions of observation have actually managed to encounter that? You mentioned X-rays and now radio. And then the other question was, how much data do you get from the Doppler effect in any of these objects? Is that how you get some of the depth?
So radio and X-ray are the only ones that I know that have gotten into the confusion limit. However, the analogy is not that far. If you think about looking at the Milky Way, or when Galileo looked at the Milky Way, why do we call it the Milky Way? Because in every patch of the sky, there appeared to be light, but it really was just smeared out stars. And so when you look at very dense regions in the sky, you take a picture in the galactic plane, you will get confused. And because there'll be something in basically, there's no dark sky. That's the point. Yeah, right. So any situation you're in where there's no dark sky between the sources, you are in what we would call the confusion limit. And there was a second question. Oh, the Doppler effect. In the radio, the answer is typically no, because the spectrum that I was describing is a continuum spectrum. It's like looking at a black body. A black body is a continuum spectrum. You can't get a Doppler shift out of it. You would confuse a little bit of color change due to the Doppler effect from just a slightly different temperature. They would be, in fact, mathematically equivalent. What you need is spectral lines. And typically, for at least the work that I do, no spectral lines. Now, there's people that work in the millimeter part of the regime, and sub-millimeter or several millimeters that do look at molecular lines. People look at neutral hydrogen. So people studying neutral hydrogen in galaxies, which is not what I was showing tonight. But yes, there they use the Doppler effect and they can map the rotation of galaxies and things like that. The 3D stuff that I was showing you has no lines in it. And what I was doing was that, and I had a slide, but I just didn't have time to say it, was that when you take polarized radiation and you put it through a medium, we get an effect which we call Faraday rotation. The polarization angle rotates as it goes through the medium. And if you pick your areas carefully, you can figure out how much rotation there was and therefore figure out how far back it came from. And that's what I did. I looked at each piece and said, how much rotation have you experienced? And then said, that's equivalent to how far back you were inside this medium. And we'll see whether the referee buys it or not.
Okay. Before we go to any questions online, any more questions in here? Okay. Wait. People online can't hear.
Okay. I was just wondering, I assume you guys are doing circular polarization also. Do you get estimates of the strength of magnetic fields around some of these structures?
Yes, we are doing circular polarization. It doesn't really apply in the sources that I was showing you. Their circular polarization is near zero. Everything is very symmetric, but when you get to very compact objects, some of these things on sub-parsec scales and stuff like that, where most of the emission is coming from close to the black hole and the magnetic fields are very strong, you can get circular polarization. And so, yes, people are doing that now. They're not making pretty images because once you get to one of these distributed sources, the circular polarization goes to zero. But when you get down to the nucleus where the fields are very strong, and stars, there are stars that you can see in the radio and see circular polarization. So there are isolated places where, yes, people are doing it, and they would be angry at me for being so dismissive that you can't see it everywhere, because for them it's very exciting. And so, yes, there is circular polarization, just not from the things that I showed you.
Any questions? Any other questions? One more question, Anton.
Do these, is there application here for 21 centimeter cosmology? Could they, the Dark Ages, Cosmic Dawn?
Absolutely. So let me just explain a little bit the question. The universe started out as complicated plasma, and 380,000 years after the Big Bang, we went through what we called recombination, where the universe cooled enough so that the hydrogen could recombine and the electrons and protons could get together and form hydrogen atoms again. That didn't last. We went through a time which we call reionization billions of years ago, where the first quasars, the first very massive stars, various things were going on, shooting out high enough energy radiation that it reionized the universe. And once you reionize, you don't get the hydrogen line anymore. You don't have hydrogen. So people that use the hydrogen can watch that process happen. They can start at the time when the hydrogen atoms formed at 380,000 years after the Big Bang, when the temperatures were about 3,000 Kelvin or so, time of recombination. They can see the hydrogen. It's heavily redshifted. I mean, way, way down, very high redshift. But then they can watch as the hydrogen starts disappearing and find little holes. It's like, oh my gosh, there's a quasar. And look, it's a vacuum, it's destroyed the hydrogen around it. So that's the game. And we're going to start that game by detecting statistically how much hydrogen, how the hydrogen disappeared as a function of time, and then eventually make maps and be able to see these little holes in hydrogen and figure out how the reionization happened. So yes, it's a big part of the business that people are interested in.
There was one request that we hear how it comes out after the refereeing process.
Okay. I'll let Mark know.
Yeah, go ahead. Just send it to me.
Yeah.
Are there any other questions online? If there's anybody that has a mic and has a question, they can open their mic. Dean has another question in here first. That'd be a follow-up to your follow-up,
Yes, sort of. With reference to your paper being refereed, not trying to embarrass you or anything, but what are you most worried they'll pick on?
What? Say it again.
What are you most worried they will pick on with your new method?
I think that a lot of the analysis that we did in the paper is non-standard. So this is this really interesting dilemma. Just like I said, you need to stay flexible and open to new things. That applies to the kind of analysis you do as well. And so in the paper, we do several kinds of analysis, including this 3D deconstruction that don't appear already in the literature. So the referee may look at that and say, no one's ever shown that that works before. And to which my response would be, got to start somewhere. I mean, what they have to do is to see whether we made reasonable assumptions. The biggest challenge will be, did we make reasonable assumptions? And the answer is, some of those assumptions we can't justify. We have to say, we are assuming this for simplicity's sake, and now we're going to explore the implications of that if we assume that. I can't guarantee that those assumptions are right. A referee may like that style or not like that style. And so it could get ugly. I don't know. But my tenure doesn't depend on it anymore. I'm retired. I can even no, I won't call them names. Okay. It's all anonymous, by the way. You don't know who's refereeing your paper.
All right, everyone.
I have a question.
Okay, I guess there is a question online.
Yeah. This is Dave Evans. How can JWST and your research with SKA complement each other?
Yeah, I think JWST is going to be giving us a window on the very first stars that are forming, the first structures. And in the radio regime, we're probing that same era. So it's two different views of what happened at the earliest times as structures starting to form. So I think they're going to play nicely together.
Anyone else? All right, everyone, it's late. We probably should get out of here so they can clean up. Thank you, Larry. And please let us know about the paper. And please come back again. And then I was just getting to that. So on your way out, drop your vote off with Steve. And I'll let you know, because we're going to go analyze what the online stuff was and what we have here over a couple beers, maybe, or 6. And then we'll let you know. But rest assured that if it doesn't happen, I'm going to be letting you know. And what I'm going to ask you to do, I'm going to challenge every one of you that's still online, that's still in this room, is when you see my email asking you to show up, you send a reminder email to 10 people that you know that you did not see here tonight and ask them to be here. And if they run online, you know, they only have to show up until we're done with our spiel and they vote. Then they can go away if they want, if they don't want part of the program. We're just asking for 10 or 15 minutes of their time. I mean, we can accomplish this. It doesn't mean that you have to be present at the meeting, but you don't have to stay the whole time. So thank you, everyone. Thank you for your patience. See you next month. I'll be here for sure. And have a good night and have a good month. Happy Independence Day, by the way. Good night.